look at some examples of completing the square, I want to unpack why it works. So say we have x squared plus bx, and I'm going to represent them using area. So we have x squared here, and we have bx here. Now, we could rearrange these shapes and try and make one big square. And to do that, I'm going to cut the bx shape in half and add half to the side and half to the bottom of the green square. And because we've cut it in half, we could say that each of these lengths here are half of b, or b over 2. And if we could include this last little corner, then we could find the area of this new square by saying x plus b over 2 all squared. So what's the area of this last little corner? Well, if this is b over 2 and this is b over 2, then this last little corner has the area b over 2 squared. You should hopefully see now that the shapes up the top, if we added the area of all of these shapes together, we would get the area of the big square down the bottom. So we can now say that x squared plus bx plus b over 2 squared is equal to x plus b over 2 all squared. And adding that last little corner is called completing the square. And that's because when we look at the second shape, that's exactly what we did. We completed the square. So why would we do this? Because if we're looking at sketching a parabola, completing the square we can use to solve the quadratic and hence find the x-intercepts. But in the process, we have to actually put it into turning point form. And so it means that in the process of finding the x-intercepts, we also find the turning point. So we're doing two birds in one stone. So let's have a go at this example. The first step is to divide all terms by a. It's a monic quadratic, so we don't need to worry about that step. I'll tick it off. The second step is to find b over 2 all squared. And this is in the form ax squared plus bx plus c. So b is going to be 4. So we have 4 over 2 all squared. That's going to be equal to just 4. That's step 2. Step 3 is to complete the square by adding and subtracting b over 2 squared. So we have y equals x squared plus 4x, and we're going to add 4 and subtract 4 in the middle here. And we do this because we can now group these first 3 terms together and actually simplify by factorizing. This is a perfect square. So we can write this as x plus 2 all squared. And it's a good point here to actually just double check that you got this right by expanding the perfect square and making sure that you get this. But by factorizing, we could simplify this, and now I can collect the like terms out the end here. Minus 4 minus 1 is minus 5. So hopefully you can now see that we have the turning point form. And so the turning point here, we're looking for h and k. And because we've got a positive inside the brackets, h is going to be a negative value. So we have minus 2, and then k is minus 5. So this is our turning point. Now we're going to keep going and find the x-intercepts by making y equal to 0. So we have 0 equals x plus 2 all squared minus 5. Now it's just a matter of rearranging the equation. So we've done step 4, so I'll move on to 5. So we're going to put 5 onto the other side, equals x plus 2 squared. Taking the square root of both sides, it's going to cancel out the square sign. So we have x plus 2 on this side equals plus or minus the square root of 5. Remembering this plus or minus part because you need 2 answers. And so then x is equal to 2 plus or minus the square root of 5. And if you were asked to just solve the quadratic by completing the square, you should probably leave it like this. In the surd, it's more exact. But if you were asked to sketch a parabola, you might simplify by saying x is approximately equal to, and we've got minus 4.2 or 0.24, just because it's easier to sketch when you can see the actual numbers.